Okay, thank you very much. Welcome, everyone. I'm very happy to start off the school session of this program. In fact, we have an outstanding lineup of speakers, many of my friends here. In fact, so outstanding that I think it's better that you hear most of the topics from them. So I had this problem that I would prefer to hear the things that I will talk about from them instead of me myself. So I had to find something to talk about. And so this is why this is a talk that I will begin by deep diving. So what do I mean by deep diving? So deep diving is really deep diving into your memories. So we're going to talk about scattering amplitudes, but from a very old-fashioned point of view, meaning that we're going to start from quantum mechanics. Okay, so we're going to talk about a process that is the 2-to-2 scattering. So we're going to talk about 2-to-2 scattering, which means that we have a picture that we have something that there's two objects coming in, something happens, and two objects coming out. Okay? And we're going to talk about what kind of observables we want to define for this, which of course, as you know, that this will be the scattering amplitude. But we're first going to talk about how we first encountered thinking about this, which is in quantum mechanics. So in quantum mechanics, what you would do is that you think of this as, instead of this picture, which is in some sense a more relativistic picture, you think about something that is coming in with some potential here and then something going out, where this is the non-scattering part and this is the scattering part. Okay, so this is a more non-relativistic point of view. And basically what you will be doing is you will be doing something that is you're solving a differential equation. So you have a Hamiltonian, and this is the simplest thing that we set up, and we try to find its eigenstate. Now, why do I want to start with this? There's several reasons. First of all, so I framed this as solving a differential equation, right? And this has many applications. For example, in black hole perturbation theory, you can set up exactly the same equation. Okay, what is black hole perturbation theory? So basically, we have the Einstein equation, which is a differential equation on your metric. But instead of writing this as a differential equation on your metric, you separate into a differential equation on your metric plus linear perturbation. Okay? And therefore, you basically have a first order differential equation, let me call it an O, acting on h mu, and you're trying to solve some kind of, let me just call it as lambda h mu, and you try to solve its eigenvalue function. So since black hole perturbation is solving an equation that looks exactly like this, that means that from black hole perturbation, you can also set up the scattering amplitude for this process. Okay? So this has many applications, in fact. And we're going to start with how to set up what do we mean by scattering amplitude in this framework. And then we'll connect this to our usual, or some of you who are more familiar with the quantum field theory formulation of the S matrix. Now, just beforehand, you might ask that what is the relation between these two? And in some sense, you can view this from what the relation is from this picture that I just draw before. So this would be my QFT version, and this would be my quantum mechanic version of the same process. And if you look at these two pictures, then you can see that basically the quantum mechanic version of this problem corresponds to, I'm treating this one of the states as a source that is sourcing the particular potential that I have. So in other words, that's why quantum mechanics is called first quantization, right? It's considering the quantum mechanic behavior of an object with respect to a classical background, right? So that means that to go from here to here, I'm basically taking what is called the probe limit of my quantum field theory observable. Okay, what is the probe limit? That means that, for example, if I consider these have two masses, let me call this M1 and M2, then that means M1 over M2 is very small. So that this is like a heavy source that is sourcing some background, and I'm just computing the scattering amplitude of this bouncing off that background. So that's basically the relation between, the relation that I'm going to invoke between quantum field theory and quantum mechanics. Okay? So that's why I want to start with quantum mechanics. I want to start with quantum mechanics where we can set up this problem and then you can apply this in many other contexts, which other speakers will talk about. And we'll also very quickly get some idea about some general properties of this, scattering amplitude. Okay, good. So we want to solve this equation, and usually this is where if you turn to any of your quantum mechanics textbook, then usually in the scattering problem, people will start with the Lippmann-Schwinger equation. And that's basically you're trying to write your scatter state. Let me use this notation. So this is your wave function as this is the momentum eigenstate, which corresponds to, let me just pick this picture here, this K vector here, plus and this is the scattering potential. Okay, so this is the solution to your Schrodinger equation. A formal solution, of course, because the same states appear on both sides. But of course, the idea is then you do perturbation series. You do iterative perturbations to write this down. Now, this plus here is related to your I epsilon prescription, which is basically setting it up such that when t goes to minus infinity, this state will reduce to the usual plane wave. Okay, so that's related to this I epsilon prescription. Of course, you can also choose the minus prescription, which sets up a boundary condition at t goes to plus infinity. So this tells you that already the fact that you have this plus means that you need to set up the state. I need to set up the state with a boundary condition at t equals to minus infinity, which will come importantly in how do I set up this when I try to do it in quantum field theory, which is what are the asymptotic states for those of you who are familiar with this. Okay, again, this is everybody knows this, so I'm just really reviewing things that you've learned in quantum mechanics. So you basically in quantum mechanics you will solve this, and of course you want to look at this position space form of this wave function. So we sandwich it with x. And then here we will, sorry, let me just erase this. And here, instead of this, we will write, as you sandwich both sides with x, this becomes integration over dx prime with the free Green's function, dx prime, and then x prime. Okay? Very good. So now, so basically from this point of view, we have the usual picture that you have in your textbook where you have some potential which has some finite range here. And basically from this, you can see that we have the picture that the scattering function here, which is of distance x, and you're integrating over the distribution of your potential in x prime. Okay, so this is x and this is x prime. That's why you have an integration over x prime. This has a very simple, picture. We can, if you assume that your potential is finite range, that means that at certain at long distance, the potential essentially shuts off. Then we can see that this wave function at x goes to infinity, or maybe x minus x prime, sorry, or let me just write x much greater than x prime. so that the distribution of your potential is you're very far from the distribution of your potential, then this wave function will be essentially proportional to something that takes the form of exponential I k dot x plus exponential I k r over r, and let me call this fkx. Okay, and this will be our scattering amplitude, because as you see, that basically this is our scattering amplitude in quantum mechanics, because this is telling you, so this will be the part of your wave function that was just initial wave function that is going through, and this is the part that is telling you how much is being scattered off into a spherical wave that is going out. Okay, and if you compare this to the original Lippmann-Schwinger equation, then you see that this function f k of x is basically proportional to the momentum k prime times v in our notation. Okay, where what is k prime? K prime is just the original, the same magnitude of momentum, but pointing in the x hat direction. So that's why I write this x hat here, where x hat is, again, is where the observable. So this is all just a review. So I can also write this. Some people like to write this directly. If you write this directly out, then let me just write dy. Okay. So as we usually have, then from the definition, the differential cross section will then just be the absolute value square of. Okay. Good. So I'm just writing down equations that you have seen before in your quantum mechanics textbook. Okay. Good. So this is our scattering amplitude. So we start with the definition of this. Again, later on, when we're formalizing, so when we write more better representation of it, you can come back here, and if you're solving black hole perturbation, which we'll mention and probably in the next lecture, I will do something similar with here. Just instead of Hamiltonian differential equations, now you have Einstein GR differential equation, and we're solving essentially the same thing. And then we'll follow through, and then we'll derive something that is basically, again, we can interpret it as a scattering amplitude. And that will now tell you about the scattering amplitude of like a gravitational wave scattering off a black hole background. Okay. Good. So another important ingredient I'm going to use in the later part of my lecture is what is called the optical theorem from this. So we can see how the optical theorem is derived here. Okay, what is the optical theorem? So it's basically telling you that the imaginary part of the forward scattering of this amplitude is actually your total cross-section, which many of you know. So let's see how you derive it from here. So since you have this formal solution there, so remember that you had this formal solution for, I guess I should bring this down a little bit. So you have this formal solution for your wave function. Then you can see that instead of, if I now contract this on both sides with k, then I have that my scattering amplitude in the forward limit, which of course this function is just my f of k there. It's in the forward limit because usually my scattering amplitude is, if I write it in this form, then it's with momentum k prime, where k prime is k in the x direction. But instead, now I'm contracting it directly with k, which is the original incoming momentum eigenstate. Then if I instead contract with k, then just using repeated use of the Schwinger-Lippmann equation, then you can see that it's equivalent to this. Okay, to see that you can write it in this form, all you need to remember is that in our original form here, in our k, you can just put k into the left-hand side and then put the psi plus onto the right-hand side. And that will be your k here. And then you can do the contraction and you'll get this equation here. So I want to take the imaginary part of this. Now, if your potential is real, then this will contribute nothing to the imaginary part, obviously, since this is manifestly real. So the only place you can get imaginary part is coming from here, right? And to get the imaginary part, you can think of this as an integral over E, and that tells you that the imaginary, from that you can see that the imaginary part, so the imaginary part, let me just write it in a simpler form, of k0, because this is the forward limit, because the k's are aligned. So it's going to be just coming from the residue of E minus H naught, which comes from the I epsilon part. Okay? And of course, I can put a complete state of momentum eigenstates in between. And so this becomes integral dk prime 3. And this is absolute value So I'm just putting a complete identity here, which are momentum eigenstates. And of course, I have a delta function here. And let me just assume that this is just free particles. And that this is just E minus H bar squared K prime squared over 2m. Okay? And this is nothing but, again, that the scattering amplitude square. And so this integral gives you the total cross section. Therefore, if you work out then you see that this is 4 pi times this total cross section. Okay, so this tells you that the imaginary part of the forward limit is going to be equal to the energy, K is related to the energy, times the total cross section. Importantly, since this is a total cross section, we derive a very important thing that we'll continue to use later on, which is this is actually positive. Okay, if you have any non-trivial scattering, then the total cross section is positive. That gives you a constraint on the imaginary part of your amplitude. The imaginary part of your forward amplitude is actually going to be positive. Okay, so this is very important. Let's just do a quick example and see what the scattering amplitude look like, and you'll see that this is actually very close to the relativistic form. Again, these are all in standard textbook. So let's consider an example. So first of all, we will use what is called the Born approximation or the tree level approximation. And what that means is that at leading order, I'm going to replace my wave function here by just momentum eigenstates here. Okay, so that's the leading order. Since you already know that at leading order, if you turn off the potential, then this is just the momentum wave function. So at leading order, if you want to consider the first correction associated with your potential, then it just corresponds to setting this wave function to your momentum eigenstate. Then that means that your leading order, your scattering amplitude is going to be proportional to so k minus k prime y times vy. Okay, where this factor comes from the fact that I'm just considering a plane wave here. Okay, so this is the leading order. Usually we call this K minus, so you can think of this as a momentum K coming in and momentum K prime coming out. And so usually we call this the difference K minus K prime, the momentum transfer. We'll define this as Q, or let me call this as Q. These are vectors. And you can see that, of course, Q is going to be, or the absolute value Q, which, is K minus K prime absolute value, is going to be 2K times sine theta over 2, where theta is your scattering angle, which is how much angle you're scattering off. And, or if I square it, it's going to be equal to 4K squared times 1 minus cos theta over 2. I'm going to put 2 here. Okay. Later on, when we make this into a relativistic form, this q or minus q squared we're going to identify with Mandelstam variable t, and so this is the usual formula that t is equal to minus 2s 1 minus cos theta. And when we go to the full relativistic form, but this is the non-relativistic form of the same formula here. Okay. So this theta is the scattering angle. Good. So let's consider a very simple potential. Oh, okay. So this is breaking apart. So let's consider the potential, the Yukawa potential, which is, let me write it, mu r exponential mu minus mu r. So formally, of course, this, for those of you who are familiar with quantum field theory, you know that the Yukawa potential will be the potential that is sourced by exchanging a massive particle, where this mass is related to mu. Okay, so there's an exponential suppression related to how much is your mass. So in some sense, compared to the usual long-range force, which is just a 1 over r potential, I can formally treat this as the limit where mu goes to 0 for the 1 over r. Okay, so formally I can do that. So if I use this potential and I substitute it in there, then we can see that our, first of all, if I convert instead of x hat, but really convert it as using my scattering angle to parameterize it, then we can see that that integral, which is a function of q, it becomes 0 to infinity r vr sine qr dr. So you can substitute any spherically symmetric potential that you want. Of course, in quantum mechanics, usually we have different kinds of, we don't necessarily assume spherical symmetric, but because in most of the talks in this lecture, we'll assume there's some sort of Lorentz invariance. So in the non-relativistic limit, you will have spherical symmetry. So we always consider spherical symmetric form here. And of course, you can just directly substitute your Yukawa potential into here. And it's just a very simple integration. And in the end, you will get, with VR substituting the Yukawa potential, in the end, you'll get that your Vk theta is simply just q squared plus mu squared over 1. Okay? So for those of you who are familiar with quantum field theory, you see that this is actually just a propagator. Okay, so this is just the Yukawa coupling, the exchanging a scalar field between two external states. Okay, so this is how, of course, the theta dependence is in this q square, because we see that the q square is going to depend on your scattering angle. Okay, so this is a very simple example. Now we have an idea of what a scattering amplitude in quantum mechanics corresponds to. Now we can talk about some general properties. So for spherical symmetric potential, it will be natural to expand this scattering amplitude on an orthogonal basis. So we're going to define two things. We're going to define phase shifts and partial wave expansion. Okay, so first the partial wave expansion. Since we expect that we're scattering off something in the non-relativistic limit is going to be invariant under rotation, and the relativistic limit is going to be invariant under Lorentz symmetry. Therefore, this tells us that it is natural to expand this on a spherical symmetric basis, and therefore it has the following expansion, 0 to infinity. This is convenient for normalization factors. And then I'm going to call this, or let me just call this ALK. Okay. Or this is just the Legendre polynomial. Of course, the Legendre polynomial, the reason that you have this factor here is because your Legendre polynomial is actually orthogonal with respect to the phase space. With this orthogonality factor. So it's orthogonal with respect to the phase space. It's just these equations are just a reminder. Now, obviously, if you consider higher dimension, there's going to be higher dimension generalization of this, which is what is called the Gegenbauer polynomials, which again is just the higher dimension orthogonal polynomial with respect to the higher dimension phase space. But you can generalize this to any dimension you want. In this part of the lecture, I think in many other lectures, we're going to focus on 4 dimensions. So I'm going to stick with Legendre polynomials here. And this is what we call the partial waves. Okay, so this is the partial waves. And so if fk theta is put in this form, where did I write my large R expansion? Maybe I already erased it. So you remember, so if my fk theta, my scattering amplitude, I can do it in a partial wave expansion. Then recall that at large R, so if I let my theta, the angle theta define with respect to my z direction, then remember that in our wave function at large R, or when x is much greater than x prime, we know that our wave function has the form that it is exponential plus ikz plus fk theta exponential ikr over r. It takes this form. Now this becomes z because I've defined my theta to be the relative angle with respect to the z direction. So I've singled out the z here. Then you can see that I can now also expand. So we know that this is expanded on partial wave. We can also expand this exponential ikz on the partial wave. And so basically what you'll get is here, if you expand on partial wave, it's going to be sum L goes to 0 to infinity. Again, if you expand it on the Legendre polynomials, an exponential ikz gets the expansion that takes this form. So it's exponential ikr minus exponential minus ikr plus L times pi. This is r divided by 2ikr. So this part has this form. This has an exponential ikr. So you see that the entire scattering amplitude, this minus ikr part is going to be just the original plane wave part scattering through. But the plus ikr is going to contain the original plane wave plus the scattering amplitude. Okay? So that means that my entire wave function is going to be, again, proportional. I can pull out L, 2L plus 1, PL, let me write theta, 2ik. And then I have the outgoing spherical wave which contains the original forward part plus 2ik fk theta. Sorry, what am I writing? ALK minus ik r plus L pi. Okay, so this is just this part, but the exponential IKR you have the 1 plus the 2IK, 2IKLK partial waves. So we usually define this as our S matrix. That part is actually our S matrix. Expanded on the partial wave. So we have the SLK is going to be identified as this part. It's going to be identity plus 2I K ALK. Okay? Because this is describing basically the outgoing spherical wave. And so from the usual probability conservation, we know that how much, since this is the minus part, the magnitude of this part should match with the magnitude of this part. So that tells you that the absolute value of SLK should be 1. Okay, because the magnitude here is 1. So that means that the magnitude of this part is 1. So that tells you that your S matrix, defined in the quantum mechanics sense, has to be just the phase. And so this is our usual scattering phase. Okay? So the scattering amplitude, again, or the partial waves ALK, it is, you can write, oh, sorry, usually we have a factor of 2. This is for convention. We define it with a factor of 2. So it's just 2 delta L minus 1 over 2I. Okay. So that our scattering amplitude f of k theta must have this form. Again, this is 2L plus 1 over k exponential I delta L sine delta L times PL theta. So any unitary scattering amplitude will have to have this kind of expansion where delta L is real. Okay, it has to be real because this is coming from solving that this is just a pure phase, which means that this is real. Of course, it depends on it depends on the context of what you're doing. So, for example, if you solve black hole perturbation theory, and later on we'll see how you actually read off what the phase is. If you solve black hole perturbation theory, your phase is not going to be real. Okay, you're going to have a complex part. The complex part for your phase represents violating of unitarity, which of course happens because when you're doing black hole perturbation, there's some absorption process at the horizon. So usually, in fact, this is how people compute what is called the gray body factor for black hole scattering. And that's basically, you just solve the black hole perturbation, you derive the phase, and you pick out the imaginary part of your phase. And that's essentially your gray body factor. Okay? But if you're doing a pure quantum mechanics computation, then this phase should be real. It should always be unitary. And you'll get this phase is actually a real phase. If we have this kind of representation, then my previous optical theorem becomes trivial. I can explicitly write it out because, of course, the only so if we take the forward limit, just means that theta goes to 0. If you remember, your Legendre polynomial at theta equals 0 is just 1. So the imaginary part is just picking out this sine delta L, which gives you sine squared delta L. If you look at sine squared delta L, you can see that sine squared delta L is basically proportional to fk squared. So you can see that so you can see that that's proportional to the total cross section, which let's just write it out explicitly. So again, we have the optical theorem. So the imaginary part of fk0 is going to be equal to the sum of L equals 0 to infinity and 2L plus 1 k, and then sine delta L squared. PL theta is just going to be 1. Okay? On the other hand, we know that our total cross-section is just integrating over the phase space again of the fk theta square. So we can just plug this into here. So plug fk theta square into here. Obviously, the phase factor will cancel out. You get a sine delta square L. You have two PLs multiplying each other. You might think that you have two infinite sums in here that you're multiplying, but remember, because the PL are orthogonal with respect to your phase space integral. So this two infinite sums of L in here becomes a single sum because it collapses, and only when L is equal to L prime does it contribute. So it collapses, and of course you have this k squared here. So in the end you will get that this is just 4 pi over k squared times sum L equals to 1 to infinity, 2L plus 1. You're only left with one sum, and sine delta L. Okay, and if you compare these two forms, you immediately see that indeed we have the imaginary part of fk0 is equal to k is equal to 4 pi k times the total cross section. Okay, so this makes it manifest. The optical theorem is a manifest. So we see that the partial wave expansion manifests the optical theorem, and also we see that from here we can see that let me just erase this. So we see that because the partial wave is related to a phase, so that means that the partial wave is actually bounded. So what do I mean? So from here this is just a trivial rewriting. So I can time k times ALK, I just multiply it here. It's just if I just reorganize everything, it's going to be 2i minus a half exponential I delta L plus pi over 2. So I'm just reorganizing this equation here. And this tells me that the partial wave, so this is the real part of my partial, the real part of my k times ALK. And this is my imaginary part of k times ALK. So it's a unit circle, right? So this is a circle of radius 1/2. So the origin is at imaginary part, so I over 2. So this is I over 2 here. And the radius is 1/2. So that means this is how, so unitarity actually constrains your partial wave in a very small region. Okay? And of course, generically, what we have is if we're doing perturbation theory, that means our partial waves is very small. So when you're doing perturbation theory, you're usually living here. When you have very small delta L, you're actually living here. Okay, so this is where perturbation theory is. The full range of how big your partial wave can be is basically living in this unit circle. And so you immediately see that the imaginary part, so we see that the imaginary part of your k times ALK must be greater than 0 just from this. Okay, so this is something that we'll use constantly. That the imaginary part of your partial wave has to be positive, or the imaginary part, which is of course related to that the imaginary part of your amplitude is actually positive. But of course, this is a statement about the sum of partial waves. But here, this is a statement about the individual partial wave. Okay, so this is basically all you've learned, well, not all, but probably the highlight of what you learned about scattering theory in your quantum mechanics. The final thing that you might learn is actually how to compute the space, the space factor here. And the generic setup that you will have in your I'm just reminding you of it, the generic setup that you have in your textbook would be that you are right. You solve your wave function. Okay, so you solve your wave function. And you basically, again, for spherical symmetric potentials, usually you will write it like in this form. So you will write it as a linear combination of two Basel functions, right? Because the Basel functions are the solution to a spherical symmetric potential. The differential equation with spherical symmetric potentials. And so you will generically, we will write it with this kind of normalization. And we will be solving two coefficients. Let me call it CL1, JL plus I eta L, and CL2, JL minus I eta L. So JL and eta L is the two the two Basel functions. These two Basel functions differ by how they behave at near the origin. So one is that it behaves as 1 over r to the L near the origin, and one behaves as polynomial. You do this kind of combination because at r goes to infinity, this behaves as the outgoing scattering form as r goes to infinity, and this behaves as the minus part. Okay? So basically, you set up your boundary conditions, and you set it up. You set up the solution for two different regions. First, for the outside of your potential region, you solve the differential equation, and then inside the potential region, you solve another set of differential equations, and then you try to do matching. And the matching is the boundary conditions that you do to fix these two coefficients. Okay, and so again, similar in black hole perturbation, you do exactly the same thing. Okay, we would have in black hole perturbation, you have a similar differential equation. You also expand it on these bases. And then what you would do is you would do what is called the far zone region, which corresponds to this quantum mechanics discussion, will be the part where the potential is being shut off. You solve it there. And then the near zone will be where you have, of course, we cannot go into the black hole, right? So you'll set up a boundary condition at the horizon, and that will be the second set, and you try to do the matching on these two. Once you do the matching, you will fix these two coefficients. Then from this formula here, you can immediately see that the phase is essentially the ratio between these two coefficients. Okay, so by looking at the ratio, you'll get the phase. Okay, and so that's how you compute the phase in the general setup. Okay, and we will use this probably tomorrow. Okay. Okay, very good. So this is all I want to do about quantum mechanics, because that's all I prepare for my quantum mechanics lecture anyway. So now I want to switch to quantum field theory. So is there any questions before I do that? Yes.
Yeah, well, you call example of computing it's like really real, right? The result is 1 over x squared plus x squared. Isn't that violate? Does it violate optical scaling?
No. Well, I mean, I haven't put my I have some prescription there, and also that's leading order. Okay, good. So now we go to quantum field theory. Actually, okay, good. So now to QFT. Again, what I'm going to try to do is I'm going to try to isolate, so in what I mean by the S matrix, or my S function there. So usually in QFT, we would have that usually people introduce the S matrix by saying that what you want to compute is you want to compute the overlap between some initial state set up at t equals minus infinity and the overlap of some final state at t equals plus infinity. This state is not basically you can say that it lies in the Fock space of your theory, which includes single particle state, multi-particle state, tensor products of so multi-particle state will be tensor products of these single particle state. We'll talk about how to define these state later on. But then we switch to the interacting picture, which is basically you expand your final state on the states of your free theory, and your initial state is also states on your free theory or the asymptotic states. And then this function, this operator here is the S matrix. This is how it's usually defined. And so in order to discuss this, we need to discuss what are the asymptotic states. And if I view my asymptotic states as states associated with my single particle state or the tensor product of my single particle state, then the questions corresponds to what are the quantum numbers I can associate with my asymptotic states, right? So that's how we define a state, which is the quantum number. Now, if we don't have any other global symmetries, then the only global symmetries we have are just the Poincare symmetry, which means that we have the generators M, P mu, which is the translation generator, and then we have the Lorentz generator. Let me call it M mu nu, okay? Or sorry, let me change. Oops, just put it here. Let me call it J mu nu. Is there a question? Okay. Yeah, so these are our generators, and what do I want to do with generator? I want to find the maximally commuting generator and their Casimir. Right, that's what I want to do, and then these will be associated with my the quantum numbers I can assign to these asymptotic states. So okay, so you all should be familiar with the algebra, the commutation algebra of these generators. So now, first of all, so we can have our momentum. They all commute. Of course, once you have a momentum, you have the Casimir, which is p squared. They all so p mu and p squared commute with each other. I can also have the following: epsilon mu nu rho sigma. So again, I'm in 4 dimension. J nu rho p sigma. Okay, you can see that J will commute with. So if I look at let me write it here. So let me call this W mu. So this is basically the Pauli-Lebensky vector. And of course, then P square and W square will be my Casimirs. Now, let's say if my momentum P is 1, 0, 0, 1, if I'm considering massless, then this Pauli-Lebensky vector, there's 3 components associated with this. Then I will have my W3, let me call this W3, which is basically my J3, the rotation around the 3rd direction. And then I'll have what is called plus and minus, which is the linear combination of W1 plus IW2. Okay. So the Pauli-Lebensky vector is basically the generator that spans what we call the little group. Okay, because obviously the commutation of this with respect to your momentum is 0. So this preserves your momentum. So this is the operator that preserves your momentum. And this actually has 3 components to it. So this is usually called ISO2, which includes a rotation, the 2D rotation part, and essentially a translation part. Okay, you can view this as a translation in the two direction. And their commutator algebra is W3, W plus minus is plus minus W plus minus, which means that if you set up your state as a momentum eigenstate and an eigenstate of your J3, which we call the helicity, then W3 acts on J3 as H times, but importantly, W plus minus acting on pH will be mu pH plus minus 1, where this mu corresponds, so of course we know that the eigenvalue for p squared will be m squared, and the eigenvalue for omega squared, we call it minus mu squared. This is just convention for mu. Okay, so depending on, so this is, of course, I'm putting in the masses case, but so mass will be a quantum number, which is natural when you're scattering our states, we know that what kind of mass we're scattering it. But this is actually something that most of you might not be familiar with. This mu square is another quantum number that you can associate with the states that you're scattering. And just as usual, if you think about your SU2, if you remember your SU2, you have this S square quantum number, right? So if you have a non-trivial S squared, that means that the JZ or the SZ direction goes from plus S to minus S, and they form an irreducible representation under SU2. Here it's the same thing. If you have a non-trivial mu square, that means that the different helicity states will actually form an irreducible representation. Okay? And so this is actually the 4-dimensional little group, what the 4-dimensional little group is telling you. So if you have it, so non-zero mu means that when you're doing a scattering, you should have both helicity, you have helicity H and their other components that form an irreducible representation. Which means this is what usually people call continuous spin. Okay, so there's some discussion about continuous spin, the scattering recently, or continuous spin theory. And that's basically coming from the representation theory of your little group. Okay, of course, for us, or most of what we're going to talk about in this lecture, in this school, we'll be focusing on mu equals 0. Which means that we just have isolated helicity states that we're scattering. Okay, but I just like to point out that if you really work through the algebra, you can actually have these non-trivial representation, which is non-trivial mu squared equals 0. And so these are usually called continuous spin. It's not that the spin is continuous, it's just that you don't have isolated helicity state. They have to come in an irreducible representation. And so when you're scattering, like all these different helicity states have to scatter at the same time. They have to be present. Okay, and there's been some work that is trying to build up consistent S matrix associated with these continuous spin representations. Okay, but for us, we're just going to focus on mu equals 0. And so since we're going to focus on mu equals 0, that means that these operators do not act. I mean, when they act on it, it's a singlet. So our said another way, our asymptotic states are singlet under the raising and lowering of your little group. And essentially, we only see the W3. So in other words, we only see the SO2 part of the ISO2. So that will be the things that we will be considering. And since you see that this is essentially just the J3 component of your Lorentz or your rotation, so that means the irreducible representation for H can only be half integer. Okay, because you can view it as a component of your, let's say, your usual rotation, which is just SU2, which just have half integer or integer powers of half integer representation. So our H can only be 0 plus minus 1/2 plus minus 1 and so on and so forth. Now, I'm going to focus on H equals 0. So I'm going to make things simple. So in the remaining of this talk, I'm just going to focus on H equals 0. And so we're going to talk about scattering amplitudes associated with just 0 helicity states. Okay, so now we define our asymptotic state. So now let's talk about our S matrix or our S operator. So again, our S operator okay, unfortunately I erased it. So previously when we define our S operator, we see that there's a 1 plus the amplitude, right? So the 1 was actually the part where there's no interaction, and we have the plus amplitude. So we should do something similar to here. So our S matrix, we should write it out as the identity plus the IT operator, where T operator contains the non-trivial scattering part. Okay. For example, if we wanted to consider 2-to-2 scattering, then we can write, well, first of all, usually our T operator is written as 2 pi. We factor out, because we have Poincare symmetry, so we know that there's a momentum conservation piece. So we usually factor out the total momentum conservation part and define the amplitude as whatever that is remaining behind. And so, for example, a 4-point amplitude, a 2-to-2 scattering 4-point amplitude will essentially be, we have 3-4 particles sandwiching T and 1-2 particle coming in. So this is our, or maybe I should put the 2 pi with the 4 delta function here. So then this will be delta I equals to 1, sorry. This is 4, and then we have some I, pi here, times m to the 4, 1 to 4. And this, by sandwiching between what kind of initial states you have and what kind of outgoing states you have, you define your scattering amplitude. So in this talk, we're going to focus on our 4-point scattering amplitude, which is just 1, 2 going to 3, 4. Of course, you can have n-point amplitude. You have 1, 2 going to 3, 4, 5. That will be a 5-point amplitude. You can have, of course, then in this setup, you see that there's actually a difference between 1, 2 going to 3, 4, 5, or 1, 2, 3 going to 4, 5. It's actually different kind of scattering because your initial and final states are different. How to relate going from 1, 2 to 3, 4, 5 to 1, 2, 3 to 4, 5. How to relate these two answers is usually framed as how to do crossing symmetry. Okay, so that's a question of crossing symmetry. And we'll talk about crossing symmetry probably tomorrow. Okay, so that's basically associated with amplitude that are essentially the same number of asymptotic states, but different distribution of initial and final states. Okay, how to relate these functions together. So that's something we'll talk about tomorrow. But anyway, so we'll focus on the 4-point amplitude. Now, of course, we know that this is a physical observable, so obviously this should be a unitary operator. So we have the usually unitary equation, which is S Dagger times S has to be identity. Then if we substitute this into here, then we immediately have that your imaginary part of your T has to be equal to T Dagger T. Okay, so this is the source of the quantum this is the source of the quantum field theory version of the optical theorem. To see that this is an optical theorem, what we can do is we can sandwich. Of course, to talk about optical theorem, we want to talk about 2-to-2 scattering. So first of all, we want to sandwich it between 2 incoming states and 2 outgoing states. So the imaginary part of 3, 4, T, 1, 2. So I'm sandwiching that equation by 3, 4, and 1, 2. Is going to be equals to 3, 4, T Dagger, T, 1, 2. Okay. First of all, I can insert a complete state. Let me just call it X, meaning I'm inserting the complete physical states in the middle, which means that this becomes X, X, T, 1, 2. And then I consider the forward limit. So what does forward limit mean? So that means I have 1, 2 coming in, 3, 4 going out. I identify 3 with 1 and 4 with 2. Okay, that's what we mean by forward limit. So if we consider the center of mass frame, we have 1, 2 particle coming in. So this is, because we're in the center of mass frame, so their momentum is opposite. So we have 1, 2 coming in. We have 3, 4 going out. So in the forward limit, with the particular scattering angle, so in the forward limit, I just mean to identify 4 with 1 and 3 with 2. So that is forward scattering. So this corresponds to theta goes to 0. Okay, so that means that this becomes in the forward limit. So let me call this, so let me identify 3 with 2. So 3 I identify with 2 and 4 I identify with 1. Then this just becomes dx x p 1, 2 absolute value square in the forward limit, because now 3, 4 is identified with 1, 2. So this becomes the complex conjugate of this one. So it becomes the absolute value square. And therefore, this gives you basically the total cross section of the scattering process. So this is how you get the optical theory. Okay? Okay, very good. So now let's look at this function. So basically, let's look at how this function should behave and how does it connect to our usual understanding of deriving amplitudes from Lagrangian. Okay, so good. So now we see that we want to talk about this function m, this function m4. So I want to talk about this function m4. Now, because my asymptotics, so I've already identified that that the asymptotic states are associated with helicity 0 quantum number. So that means that this m4 can only be a function of my momentum, pi, because it doesn't carry any non-trivial little group weight. H is equal to 0. So that means that this is just a pure function of your momentum. Okay. Now, of course, we know that we want this to be Lorentz invariant. So that means that this is actually a pure function of S and T, which are the Lorentz invariant inner product. So here, my S is defined as P1 plus P2 squared, and my T is defined as P1 plus P4 squared, or P1 minus P4. So I'm going so my momentum setup is such that I have P1, P2 incoming, and then P3, P4 outgoing. Of course, most of you know that you can also have U, which is P1 minus P3 squared. But because of momentum conservation, you have S plus T plus U equals to sum over the mass, I equals to 1 to 4. Okay, so therefore you only have 2 independent variables. All right, so we have this function here. What does this function actually, what do we know about this function? So, well, first of all, we know that this function, M4S, in principle, I can write it as a function of MST, or I can use my formula before where I can remember that T is equal to minus, let's say if this is massless at the moment, so this is minus S over 2, 1 minus cos theta. Then I can also say that this is really a function of S and theta, because I can just replace T as a function of S and theta. And from our previous discussion of quantum mechanics, you know that, and since we're talking about Lorentz invariant scattering amplitude, so rotation invariance is obviously a subgroup of Lorentz invariance. So we know that this function has a natural expansion in terms of partial waves. Okay, so now again we have 2L plus 1. And again we have the partial wave amplitude. Now the partial wave amplitude itself now is going to be a function of S times PL cos theta. And since this is coming from an S matrix, so we know that again we have the property that the imaginary part of ALS has to be positive. Okay, just from the optical theorem discussion. So we know that it should have this kind of expansion. Okay. Next, we actually have some information about how this function actually looks like asymptotically. So let's consider the limit where m for st. Let's take s goes to infinity, or s goes to infinity, and s much larger than t. So this is usually called the Ricci limit, or the. So this is in contrast to large energy fixed angle, which would be s goes to infinity, but t over s fixed. So that's large angle fixed. Large high energy fixed angle scattering. But instead, we're considering a Ricci limit, which essentially is the Fourier limit evaluated at high energy. So how should this function look like? Or what do we know about this function? Well, there's actually a very simple argument that you can argue that tells you that this function is actually bounded as s goes to infinity, okay, in this limit. How do you see that it's bounded? So remember, so since we're near Fourier limit, t equals 0, and so that means in some sense we're doing large impact parameter. So you can imagine that we have two things scattering, okay? And let's say, let me call it the impact parameter, or the difference, or the impact parameter, label it by r. So let's say if the scattering potential is related to, let's say it's something that looks like a Yukawa potential, or the scattering is mediated by some kind of massive particle. Then that means that the amplitude itself should be proportional to some coupling times, let's say, your energy, which is related to what these interacting vertices are. Let me call it e to the n. But really, the relevant thing is that the dependence on r has an exponential suppression, right? Generically, there's an exponential suppression. If it's masses, then it's a 1 over r suppression. I'll talk about masses in a bit, but let's just say it's massive, then it's an exponential suppression. So that means that this scattering has to shut off once r goes to be sufficient large, right? It has to shut off. It can no longer scatter anymore. It cannot be arbitrary large distance. It can no longer scatter. Where does it shut off? Well, essentially, it shut off roughly. It shut off at r smaller than n log e over m is when it starts to shut off. Okay? So if it shut off at sufficient large r, that also means that your partial waves will not have support, because remember, the partial waves has an angular momentum L. The angular momentum L is associated with energy times this. So it's the angular momentum of this two-body problem. So it's essentially the center of mass energy times this impact parameter. It's associated energy times this impact parameter. So that also means that your partial waves is going to shut off at sufficient large L. Okay? Now, since you're no longer scattering at sufficiently large R, that means that your cross-section is, so that means that your cross-section, because the cross-section is such in very, we're doing the very worst estimation possible, then that tells you that the cross-section, which is the radius square, it's a cross-section, so it's an R square, it has to shut off at this value, right? So that means your cross-section has to be bounded. If you just substitute this in, this has to be bounded by n squared log square e divided by m. So that tells you your cross-section has to be bounded. So again, the reason that your cross-section is bounded is just because that at sufficiently large distance, you're really not scattering anymore. Okay? If your cross-section is bounded, since my imaginary part of my amplitude is related to my cross-section, that tells you that the imaginary part of my amplitude, of my 2 to 2 amplitude, has to be smaller than or equal to s log square s. Because remember, s is the center of mass energy, is associated with E here. Okay, so this is the famous Froissart bound, which tells you that at high energy, the amplitude, the high energy, so since the high energy, the imaginary part of the amplitude is actually bounded by s squared. Okay, so this is the usual Froissart bound argument. Just using the fact that my particle is mediated by a massive, or my force is mediated by a massive particle, then this means that it has an exponential suppressant, and you can immediately derive this bound. Now, of course, in many of the examples that we're actually interested in, this is actually not, the force that's being mediated is actually not massive, it's actually massless. So this is the usual problem of trying to invoke Froissart bounds on amplitudes when you're talking about massive scattering, in particular when you're talking about scattering amplitudes for example, in a gravitational context. In that case, there's various ways that you can bypass this and still get a somewhat similar to this S-squared bound. Most of these has to do with higher dimension. You can go to higher dimension. If you go to higher dimensions, then first of all, you invoke the fact that at large distances, these scattering has to, whatever the complete theory that you have, at large distances, the scattering is basically, you're doing scattering in GR. It's governed by GR. So at large distance, it's governed by GR. That means that it has to reproduce the GR amplitude, which is the Newtonian potential, which then gives you constraint on your partial waves at high L. And then using these constraints, you can derive similar bounds to this in higher dimensions or in a gravitational context. In 4 dimensions, this becomes problematic because of the fact that in 4 dimensions, our amplitudes are actually infrared divergence. So these arguments actually run into problems in 4 dimensions, which requires you to introduce some kind of regulator. For example, you can think of our space it's not exactly flat, but with a small cosmological constant as the regulator, and you have some discussion and try to try to argue for certain bounds in that context. But I won't go into details. Okay, so basically, from later on, so in today's lecture, I want to establish 2 things which I want to use. The first thing is that my imaginary part of my 2-to-2 partial waves, this is S, sorry, of my 2-to-2 partial waves is always going to be positive. And essentially, I'm going to assume that my imaginary part of my amplitude is always going to be bounded by S squared at large energy in the Ricci limit. Okay, so it's going to be bounded by S squared. This will become importantly useful. Okay, good. So first of all, we established that the asymptotic limit in the Ricci limit is bounded by S squared. Now let's instead look at the low energy limit. Okay, I have 14 minutes left. So my 2-to-2 scattering at low energy. So let's say T is smaller than 1, where 1 is normalized by some scale. So this is very low energy. Then we expect the amplitude to have the following form. So first of all, we're considering S and T small. So for example, it can have singularities in S and T when S equals 0 and T equals 0. So it can have singularity that looks like S singularity plus T singularity plus, let's say, S plus T, which is U singularities. Okay? The residue of these singularity might still be kinematic dependent. So let me just write a residue here. In principle, I can have a Taylor series expansion. I'm going to write it like this. It'll become apparent why I'm labeling like this. So I'm summing over KQ, where Q is smaller than or equal to K. So let's say that the only singularities that I have at low energy are these poles. And if I only have these poles, then I can have a Taylor series expansion. So I have a Lorentz representation of my amplitude, okay, near ST equal to 0. If I assume this, what does that mean? Well, first of all, you might ask, why am I starting at S1 over S? Why not 1 over S squared? Why not 1 over S fourth or infinity, right? So first of all, the reason that you have 1 over S, 1 over T, and 1 over U is because most of you know that I'm going to think this is a quantum field theory. And so these poles corresponds to the process where you have two particles coming in, you produce an on-shell state, and then two particles are going out. And this 1 over S corresponds to the propagator of this on-shell state in your Feynman diagram analysis. So, and for unitarity reasons, that it is usually argued that your propagator can be at most 1 over p squared and cannot be higher. And that's why you only have 1 over S, 1 over T, 1 over U. So even though you can have a Lorentz series, but the Lorentz series really only starts with 1 over S. This NS, NT, NU, so these are kinematic functions. So this can be a function of T, this can be a function of S, this can be a function of, okay, let me just call it T. So this tells you what kind of spin is being exchanged. Okay, so if you have a scalar particle being exchanged, then NST is essentially just a constant. If you have a spin L particle being exchanged, that means that NST is essentially proportional to a polynomial that starts at T equals L. Okay, how do I see this? Well, it's very simple. So we know that since this is a pole, that means I can sit on whatever that is sitting on top of this pole is fixed by its residue, right? So I can sit at S equal to 0. When S equal to 0, that means that this particle, so let's say this is 1, 2, and this is 3, 4. So when S is equal to 0, this corresponds to this propagator become massless. And therefore, since this is massless, this becomes an on-shell momentum. Okay, so the residue is given by a configuration where these are on-shell, and this is on-shell. So, and for example, in this residue sitting at S equal to 0 has to correspond to essentially a product of two 3-point amplitudes, where this is 1, 2, and let me call this P, this is 3, 4, where P squared is equal to 0. So this is a product of 3-point amplitude. So what is this product of 3-point amplitude? Well, it depends on what is the spin being exchanged. So let's say this is let me just draw this bigger. So let's say you have a spin L being exchanged. So the 3-point amplitude here on the left-hand side will be some 3-point amplitude. Let me just write it as M3 with P1, P2, and some momentum P, which let me put an L here, that is spin L. Okay? What does this amplitude look like? I claim that this amplitude can only look like one thing. It's just one, you can only write down one thing. P1 minus P2 mu 1, P1 minus P2 mu 2, all the way to P1 minus P2 mu L times mu 1, mu 2, all the way to mu L. This is what the 3-point amplitude looks like. Okay, let's take a look at what is this object. So first of all, this is what we call the polarization tensor. And this is a spin L polarization tensor because I have L indices here. So this is a spin L polarization tensor. Okay? Since this is an amplitude, this has to be Lorentz invariant. Right? So that means that these indices has to be contracted. It has to be contracted with some vectors. The only vector that you have in this problem on this side is just the momentum P1. You have this momentum as well, but this momentum is just, from momentum conservation, is just sum over P1 plus P2. So you really only have P1 and P2 to serve as a momentum, as a vector to contract with this. There's really only two combinations for the two momentum, either P1 plus P2 or P1 minus P2. Right? Any other is just a linear combination of these two. For P1 plus P2, dotted into here because of the transverse condition, usually we have that P1 plus P2 mu contract with the epsilon mu blah, 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 has to be 0 because this is a transverse condition for your polarization vector. So that means you cannot choose P1 plus P2. It's going to be 0. So the only thing you can have is just this. So this is the unique amplitude that you can have. So basically this residue here is essentially, I can write this as a sum over, let's say if it's a Spinell's exchange, so this is, let me just call this x mu 1, x mu 2, all the way to x mu L times epsilon mu 1, mu 2 to mu L, multiply by y, let me call this nu 1, y nu 2, all the way to y nu L, epsilon nu 1, nu 2, all the way to nu L. Okay, where x is just, x mu is just P1 minus P2, and y mu is P3 minus P4. Okay, it's coming from here and here. This sum is summing over, let me call it I. So I'm summing over all the possible polarization tensors here that are in between. If you sum over all the polarization tensor, you can see that this sum, summing over all the states, is just going to be an orthogonal sum. It's going to give you a tensor product. It's going to give you a product of Kronecker deltas. Okay, so it's going to give you a product of Kronecker deltas, and so this is essentially going to give you a product of x dotted into y's. So this object here is going to give you something that looks like x dotted to y, a polynomial function of x dotted to y, where the maximal power of x dotted to y can, this is, let me write it L, the maximal power of x dotted into y is L, right? Because you have Lx is here and Ly is here, so maximum power of x dotted into y is L. What is x dotted to y? So if you write x dotted to y, you can see that this is just nothing but u minus t. So that's why I say that your numerator is going to be a polynomial of t to the lth power. This L is going to depend on what is the spin that you're exchanging. Okay, so if you're exchanging a spin 0, that means that it's a constant. If you're exchanging a spin 1, that means that you have t to the 1 power. If you're exchanging t, if you find that your NST is a polynomial of t to the 34, which you will see in string theory, that's how it looks like, then that means that this that you're exchanging something that involves the highest spin to be 34. But you can also have lower spins. Okay. You can also have yeah. Actually, this is massive. We're not assuming this to be massive. This is actually massive. This is actually, sorry, yes, I should be, when I'm invoking this is really a massive discussion. Yes, this is really a massive discussion. Of course, right now we're sitting on a massless pole. For massless pole, then it's the usual that the 3-point amplitude, for the massless interaction which will be discussed probably in the next lecture, that they're completely fixed, so you also know what the numerator is. If you have s minus m squared t, if the residue or if the pole is at m squared, then that means that the exchange thing is a massive state. Then this argument goes through for the massive state. For the massive states, since the 3-point amplitude is completely fixed, you can also see that it actually the numerator, the t dependence will also follow this pattern here. Okay, so if you assume that your low energy form has this kind of Laurent expansion, so this will be the last comment that I want to make, and then we'll stop here for today. Then what that tells you, what this corresponds to, is that you're really thinking about an action, a Lagrangian, a scalar Lagrangian, where, of course, this scalar Lagrangian can have, will have, let's say, that takes this form. Okay? Notice that I'm writing covariant derivatives here. So this d mu can be gauge covariant derivatives, or gauge covariant in terms of a massless vector, or a gauge covariant with respect to gravity, which it has this covariant derivative because it might have some massless exchange. So that means that it has a massless field exchange. Okay, so that corresponds to here. You might have some 3-point amplitudes that have, for example, that couples to the metric that coming from here, that where the metric will be the graviton field that is being exchanged here. So this part controls the information of this kinetic term here involving including how it interacts with the massless fields are controlling this part of the amplitude. This part, which is just pure polynomial and Mandelstam variables, corresponds to things that you can write down that looks like, for example, this. Or higher. Let's say we can have derivative like higher, sorry. Or let's say we have this, and then we have, for example, d mu. We can have two derivative. We can have d mu phi to the 4th power, and so a higher derivative term. Okay. So these terms, notice that the terms that I'm writing out here always involve 4 fields here, right? So there's 4 scalar fields. There's 4 scalar fields. This is because these are the terms in the Lagrangian that actually contributes to my 4-point amplitude. Okay, so that's why you have these, that I'm only writing down these terms here. And also, of course, they have non-trivial coefficient. Let me call this alpha 1, alpha 2. So these coefficients are what we call Wilson coefficients. And in principle, usually we should normalize it properly with respect to some cutoff, because when we write down these terms here, these are what we call higher dimension operators or non-renormalizable terms, but they're really reflecting that we're looking at an EFT. So for example, this is 2 derivatives with 4 phi's. Since 4 phi is in 4 dimension, has the same engineering dimension as, or has a sufficient engineering dimension to cancel dx4. So that means that this should be normalized by some cutoff square. And this will be normalized by some cutoff to the 4th, where this cutoff is associated with some UV completion. Okay? So basically what I'm trying to say here is that these couplings here are linearly related to these couplings here. Okay? So things that you're interested about your UV completions, which we will talk again, we'll also talk about this tomorrow, about your UV completion will show up in your amplitude in terms of these coefficients. Okay? So one of the main things that we want to talk about in this lecture is that we were going to try to constrain these coefficients here, which will be related to trying to constrain your Wilson coefficients that control your high energy, that is reflecting what your UV completion is. Now, the final comment, which I'm already 1 minute over, is that, of course, this is not entirely true that I can write it like this. Because, of course, this means that the non-analyticity associated with my amplitude is only poles. And that's why I'm writing a Lorentz series expansion. In general, this is not true. You can have branch cuts. So branch cuts are associated, it also corresponds to you have this kind of, if you write your Lagrangian like this, you also have branch cuts. So from this Lagrangian, you can compute tree-level amplitudes. Then these, of course, these will contribute to your poles, and these terms will give contact terms that are associated with your polynomial terms. But once you write this, you immediately see that you can also have, of course, loops. If you have loops, then that means where these are masses, then you mean, for example, this will give you something like log S, which obviously is not contained in this representation here. So in general, you can have branch cuts, and therefore, when we're talking about we're trying to constrain these operators here, there has to be some mechanism where I can separate these contributions or these tree contributions from my loop contributions. in practical, when we're doing practical analysis. And this is also something that we'll discuss tomorrow. Okay, so let me just stop here. So this is basically the important point, and we'll work on this amplitude more tomorrow. Okay, thank you very much.
Never people, when you see people now you walk around people.
You mean I don't have higher order pole? I don't have t squared 2, 3.
Then the pole remain when the L is 0 or 1/2.
No, I mean this is S, right? So
Yeah.
but this is a polynomial of t.
Okay. Sorry.
Right. So if it's on t channel, then this polynomial will be a polynomial of S. So
okay.
Yeah. So I know what you're saying. You're saying that you're thinking that if this is t to L is sitting here, then there's no pole.
Okay.
Yeah.
Maybe.
No. But this residue is actually a polynomial of S. Yeah.
Okay. Maybe I misunderstood.
Yeah. Sorry.
Any other questions?
Is logarithm the only kind of non-analyticity that you?
Oh no, there's a whole bunch of zoos of non-analyticity.
I mean, to be more specific, can you have something like square root s square minus t square? I mean, to some fractional power. I mean, these kind of.
So basically, instead what we'll talk about is so here log s means when I say log s, in some sense what you're saying is that I have a branch cut from the origin, and when you're saying it's log s, you're discussing about what exactly is the discontinuity across the branch cut. So anything else, any other function, basically then the interesting discussion is not in terms of what exactly the function have, but what exactly is the discontinuity. And so then we will want to talk about what are the possible how do you constrain the discontinuity? Once you know you have a branch cut, how do you constrain the discontinuity? And of course there's many things that one can go into. So the first thing is that, of course, since you're talking about discontinuity, that means you're analytically continue your amplitude. So where are you analytically continuing from? So this is where the usual S matrix bootstrap axiomatic things comes in. You start with the physical region where you have control through the unitarity equations, and you start from the unitarity equation. You try to construct the analytic continuation from there, and you try to gain control about what exactly is a discontinuity.
Any other questions? If not, let's thank the speaker again. And in the beginning I forgot to mention one thing. This year in December there will be a conference in the
So really, we're very happy to kick off this. So this is actually a 2-year. We have a 2-year program that is in collaboration between Taiwan, NTU, LICOSPA, and in Korea in terms of Seoul National, KIAS, and other institutes where we're going to have multiple events. So this is So we start with this workshop. This year, at the end of December, or in the beginning of December, we're going to have QCD meets Gravity in Taiwan, which will be hosted at NTU. And then next year will be the big main event, which will be Amplitudes 2024, which will be held here in Seoul. And we'll also have another satellite meeting in Taiwan for next year. So this is really a series of multiple events, and starting with this workshop. So we're really excited to have this collaboration and hope later this collaboration and hope we will build more on top of this 2 year.
We will have a lunch at 12, so we have about 20 minutes to have a conversation with each other. And we will move to the restaurant together at about 5 minutes before 12 o'clock. Okay?